Hi, welcome to this presentation on the topic of Safepoints. My name is Marcus Granlund. I work in the HotSpot Java Virtual Machine team in the Java Platform Group at Oracle. In this presentation, I will present the concept and the implementation in the HotSpot JVM of what is termed a Safepoint, which is a very pervasive and specific technique used by many runtimes that provides some form of automatic memory management. I know some of you might be new to virtual machine technology and development, and as we all know, trying to dig into a new code base can be a daunting task. Because code promotes details and local concerns over high-level design, it's easy to get overwhelmed when staring at the many disparate classes, functions, macros, styles, and comments, as one desperately tries to infer some structure to help explain how all the details connect. For example, in the HotSpot JVM, we have a number of different garbage collectors. We have at least 2 different compilers, and there's an external compiler interface called JVM CI. There's a pervasive runtime component acting as glue between subsystems. There's a number of different interpreters. There's a large implementation to support native code, also known as Java Native Interface. Debuggers and profilers interact with the JVM using the Java Virtual Machine Tools interface. And there's also the JDK flight recorder system for profiling, monitoring, and debugging. And like a jewel shining at the core, there you will find the Safepoint. And the mandala is a geometric configuration of symbols. And in various spiritual traditions, mandalas are used to help focus the attention of practitioners and adepts as an aid in meditation. And as we can see, every subsystem in the JVM is related to Safepoints to a greater or lesser extent. And I would argue that when writing code for the JVM, one of the lessons you will learn over time is to always keep in mind questions like, how does this code relate to Safepointing? Is my thread running in the correct Safepoint state? Does my code introduce latencies for the JVM in reaching a Safepoint? So the Safepoint is always there. It's at the forefront in the design and implementation of JVM features. So this presentation will focus on how the Safepoint concept is implemented in the HotSpot JVM. What I have tried to do is to let the Safepoint mechanism surface at least some parts of the structure that one is trying to discover when looking at the code. And for this reason, I will try to introduce several VM components by their name, if not their full semantic definitions, and sort of to hang them on the structure provided by the Safepoint skeleton. This approach means that the presentation is not the be-all and end-all for everything related to Safepoints, but is instead an introduction as to why some things look the way they do in the virtual machine. So I will veer more horizontally than vertically to give more breadth and for the chance to introduce additional VM components. So for example, this presentation will not go into details about the derivative technologies such as handshakes and stack watermarks, but hopefully it will be easier to understand those technologies building on top of this foundation. So first, we will need some vocab. Here are a few definitions. So first, let me clarify what is a Java thread. It is a specialization of the thread concept in the JVM, one that can execute Java code. A thread local GC root is defined to be an OOP, that is, a pointer into the Java heap that is local to a Java thread. The denoted Java object on the heap is a root of a reachability tree. Mutable thread state is a state where the Java thread can mutate the Java heap, for example, allocating objects or setting fields, or its thread local GC roots. And this state is also sometimes referred to as an unsafe state. So what is a Safepoint? Well, as a noun, it is a global JVM state. And the intuitive notion here is that at this point or state, the Java world is stopped. So it's therefore safe as in exclusive access to inspect and process by the JVM. More technical definition is that no Java thread is executing inside or can transition into a thread state classified as mutable. The other part of the technical definition is that the thread local GC roots for all Java threads are made accessible or published to the JVM. Safe pointing as a verb, also known as stopping the world, is a JVM process or mechanism to reach a safe point. And there's an older intuitive notion that this revolves around the process of halting or stopping all executing Java threads, which is okay for an abstraction. But today we will learn that this is a much more refined and evolved mechanism, which rely heavily on cooperation between threads using a technique called cooperative suspension. Cooperative suspension is a poll-based technique. This means that Java threads will check or poll thread local state at designated locations in the VM. On suspension, the JVM blocks Java threads from transitioning into thread states classified as mutable. And also on suspension, the JVM triggers Java threads to transition from a mutable into an immutable thread state. And as a consequence of this transition, the thread local GC roots are published. Traditionally, bringing the system to a safe point has been a necessary evil for runtimes that provide some form of automatic memory management. And the reason for this is that this is one of the main sources of latencies and non-determinism in a runtime. So let's not be deceived by the central role of the safe point that was placed at the core of the mandala slide. So if I dare to stretch the Oriental analogy a bit further, safe points are like samsara or dukkha, in that we would like to get rid of them to reach nirvana. Recent JVM developments, especially in the GC area, have moved even closer to obviating the need for the global JVM state. But since its tradition and its central functionality in the VM, there's of course a lot of machinery in the JVM to support this. There are new derivative techniques, for example, handshakes and stack watermarks, which are more lightweight or granular in a refined use of the SafePoint machinery, more peer-to-peer in a sense. And if we do an analogy to stopping the world, perhaps an analogy would be stopping a country. So who needs to perform a SafePoint? But traditionally, of course, most GC algorithms have had the need to issue a SafePoint for at least some parts of their operations. But other activities also require the Java world to be in a stable, unchanging state. For example, thread dumps, bulk de-optimizations, biased locking revocations, which are now obsolete, a lot of various JVM-TI functionality like class redefinition and retransformation, heap iterations, etc. Also, JFR does a SafePoint to evolve a global epoch. A Java thread has a field called thread state. The purpose of the thread state is to keep track of which part of the code the Java thread is executing in. This is the state machine for the Java thread. And we can further classify it into the following categories. A mutable thread state. It's a state in which the thread can mutate the Java heap or its thread local GC roots. An immutable thread state is a state where the thread can do none of these things. Then we also have transition states, which act like bridges between the mutable and the immutable states. A transition state has a SafePoint check or a poll instruction, together with appropriate fencing. Let's, for example, take a look at this situation. So we have a new thread comes into being. It starts running in the VM state. Let's say this thread now wants to execute some Java code. In order to do that, it will need to traverse a transition into the Java state. And as the transition, as we said, contains a Safepoint check. Some notable transitions here is that the Java code can transition to state VM and to state native without performing Safepoint checks. Instead, the Safepoint check is performed when the thread returns to state Java. Another important takeaway here is that code executing in state native is considered safe. This means that during a Safepoint, Java threads can actually continue running native code. And this also means that, counter to the intuitive notion that a Safepoint involves blocking or halting all Java threads, it only means that they do not execute in a sensitive mutable state. So let's see what this amounts to. In our definition of a Safepoint as a global JVM state, the second clause was that thread local GC roots for all Java threads are accessible or published to the JVM. All current garbage collectors are tracing collectors, which means they follow or trace the reachability trees starting out from what is called a root set. That is, a set of immediately available OOPs. A proper subset of the root set is the set of roots that is local to and reachable from Java threads. Let's take a look at what some of these thread local GC roots are. A Java thread has a field called active handles. A local JNI handle provides indirect access to an OOP for JNI code running in state native. But allocating, deallocating, and even dereferencing a JNI handle involve first performing a VM state transition, which will perform a Safepoint check. Local JNI handles are auto-managed. So when the code returns from a JNI method, that is, it transitions from state native, doing a Safepoint check, into state Java. The local JNI handles allocated by that method are deallocated. The Java thread also has a field called handle area. And handle area and its companion, the handle, provides pretty much the same indirection functionality as a local JNI handle. But these are targeted for code running in the VM state. The important difference is that these handles are not auto-managed, but instead must be manually managed by the programmer. Handle marks are used to describe a handle scope, and the handle mark destructor will deallocate the allocated handles for that particular scope, and the scopes can also be nested. The thread also has an embedded struct called the anchor field. It consists of 3 pointers: last Java SP for last Java stack pointer, last Java PC for last Java program counter, and last Java FP for last Java frame pointer. The last Java frame is the entry point for external stack walking. We exclude JFAR sampling. It is set if a thread has at least one Java activation record or frame on its stack, and it's currently not in state Java. So the LGF is set in state Java before the thread transitions out. And conversely, it is cleared upon thread reentry. The anchor struct here requires only that the last Java stack pointer is set, as the other fields are either not relevant for that context, or they can be derived by the stack walking code. Java frames on the stack may contain ordinary, narrow, or derived OOPs. So if we compare to the handles we discussed previously, these are naked OOPs, that is, they do not have a handle in direction. They are direct pointers. An ordinary is a regular OOP, A narrow OOP is a compressed version of an OOP. It's a 32-bit size OOP. And the derived OOP is a pointer into an object, not pointing directly to its header. So for example, we can think of a pointer that points out an element in an array. And a derived OOP is always associated with a base. For a specific code position in Java, for a specific code position like a program counter, which stack slots and registers contain OOPs relative to that PC is described by a piece of metadata generated by the compilers, something called an OOP map. And to pinpoint an OOP in a frame, the OOP map describes a location using a relative address, either from the frame stack pointer or as an index into something called a register map. Not all code positions have OOP maps. They are mainly associated at call sites and Safepoint poll page instructions. For stack walks, the return address of each frame will be associated with an OOP map. A thread executing Java code also has a CPU context. And per the calling convention and for performance reasons, the OOPs are ideally placed directly into registers by the register allocators. HotSpot widely employs something called stubs or stub routines, which are special platform-specific assembly helper routines. An important feature of most stubs is to save the CPU context when a thread leaves or suspends its Java execution and restoring it when the thread re-enters, resuming execution, in a manner analogous to a context switch. A register map is used to resolve a location that is described by an OOP map to be in a register. There are a few more thread local GC routes, such as potential pending exception and some JVM related state, but I will not detail those further here. Let's now take a detailed look at the process of bringing the system to a Safepoint. So the process is initiated by clients that request Safepoint operations from the VMThread. And it does so by enqueuing objects of type VM operation with a property evaluate at Safepoint set to true. And the VMThread will wait for, dequeue, and initiate the Safepoint process to serve submitted requests. So this is the first part run by the VMThread. It consists of 3 parts. 1, arming the Java threads. 2, synchronizing with, that is, waiting for all Java threads. And 3, when all threads are considered safe, that is, the global JVM Safepoint state has been reached, the VMThread then runs the submitted operation. Let's take a closer look at what arming consists of. The Java thread has an embedded struct, the poll data field, which consists of 2 pointers. Arming essentially means that the VMThread changes the memory protection of what is called the poll page used in the Safepoint checks. And it's changed from memory protection read-only to no access. If we go back to the original state machine, so what the VMThread has actually accomplished here by arming the poll pages of the Java threads is that it has effectively removed the capability for threads to transition into any of the red, unsafe, mutable states. So for example, it has cut the links here, it has cut the link here, here, and here. So this means that what the VMThread has done by this process, it means that it has installed an alternative or temporary state machine. However, as we said, this is only one part of cooperative suspension, which we said was that the JVM blocks Java threads from transitioning into thread states classified as mutable. The second part of our definition was that the JVM triggers Java threads to transition from running inside a mutable thread state into an immutable thread state. And as a consequence of this transition, thread local GC roots are published. So how do we change the thread? How do we ensure that those threads that are already running in mutable states? Well, for threads running in state VM, it entails waiting until a thread performs a transition by itself. There are only a few places in the VM that explicitly perform a Safepoint check, for example, when contending for a VM mutex or monitor. The premise for this design is that the Java threads should spend as little time as possible in state VM. Things are different for threads running in state Java, though. We cannot afford waiting for threads in state Java to transition out of their own accord, like we do for state VM. A thread could, for example, be executing an infinite loop, which is perfectly legal. In that case, the JVM would never reach a Safepoint. So to solve this problem, there needs to be a mechanism in place for evacuating or ejecting the threads that are currently running Java code. Let's say we have some Java code, for example, this code, which maps an index onto the corresponding number in the Fibonacci sequence, the iterative version. But before we go into the details, it might be good to say some words about the x64 calling convention, or the application binary interface, as well as the HotSpot Java calling convention and how they are related. The Windows Platform ABI passed the first 4 arguments in registers in the order listed, and the rest is being passed on the stack in the order of right to left, or RTL. There's also 32 bytes shadow stack area that needs to be allocated by the caller. The System 5 ABI defines that arguments are passed in these 6 registers, while the rest is passed on the stack, also from right to left. And there is a 128 bytes red zone below the stack. The HotSpot Java calling convention defines 6 registers for passing arguments, also on the Windows platform. The rest is passed on the stack from right to left. There's a customized version of stack protection, one that is only really applies to System 5 platforms. And for all of these, the stack needs to align on 16 bytes boundaries. If we take a closer look, we can see that the HotSpot Java calling convention is a shifted or rotated version of the platform ABI. This shift or rotation is because by skipping the first ABI register, we can call non-static JNI methods without having to shuffle the arguments. Instead, we only place the JNI env pointer directly in the first ABI register. Most registers are considered volatile. That is, the caller must preserve registers over calls, except for the RBP register, which is callee saved. The R12 contain the Java heap base if compressed oops are in place, and the R15 register hold the current thread. So these registers can be considered constant. So let's now take a look at this Java code. This is the JITted code for the Fibonacci method with slow debug, no inlining nor loop unrolling. And I have also removed some frame setup code in this listing. Since this is Windows, we can see that the first argument comes in as EDX. But this is a bit strange. Did we just not say that the first argument was in RDX? Why is this the case? The reason for this is that the argument to the Fibonacci method is a Java primitive of type int, which is always 32-bit or 4 bytes wide. And EDX is an alias for the lower 32 bits of the RDX register. We also see that the first instruction here spills the argument to the stack. And the reason for this goes back to the calling conventions we just talked about, because the method will invoke another method called getSuccessor. And for that, the RDX or EDX register will be needed in that call. So since the registers are considered volatile, it's up to the caller to preserve the value over the call. And as we can also see a bit down below, the JIT compiler has inserted a Safepoint check or a poll instruction into the regular code stream. And it consists of two instructions. One is loading the poll page pointer from the Java thread, which resides in R15. Then a test dereferencing the poll page is executed. In addition to inserting the Safepoint check instruction in the code stream, the JIT also ensures that the test instruction here has an associated OOP map. But for this particular example, that particular OOP map would be empty. But the reason for this is that because this code does not really use any Java objects, any OOPs, because it's a static method. That is, it has no receiver object, and it only works with Java primitives. Safepoint checks are inserted by the compilers into loop headers, like this one here, to capture long-running loops, and just before method returns. Let's inspect the callee method, getSuccessor. Here we can see that the Safepoint check instruction is a bit different. It's a compare and jump instead of a test. This is a more optimized version of a Safepoint check, and it's related to the derivative techniques such as handshakes and stack watermarks. Unfortunately, this version cannot be applied in all contexts, and we will see just in a minute why we need different polling instructions in different contexts. We also saw that on the previous slide that together with inserting the Safepoint poll test instruction, the JIT had also provided an associated OOP map for that location. But in this code here, the Safepoint check compare instruction does not have an OOP map associated. Why is this? So this is because the Safepoint poll instruction at the end of methods is inserted after the frame has been popped, but before the return instruction. This means that the caller's return instruction is on top of the stack, and by representing a call site, it has an associated OOP map. If we go back to the caller, we can see here that this Safepoint check, that is a test instruction, tries to dereference the poll page it has loaded from off the Java thread located in register R15. But what if the VMThread has armed the poll page? That is, it changed the memory protection from page read-only to page no access. An access violation or segmentation fault will be raised by the hardware, which in turn inform the operating system, which in turn inform registered signal or exception handlers. The HotSpot JVM will register signal handlers with the respective operating systems just to get notified about these kind of events. And using the information provided here by the hardware and the operating system, we can determine what kind of event took place. So in this example here, it was an access violation or a segmentation fault. And there is also information provided about which instruction caused it, and also what memory address was attempted. So inside the signal handler, we can determine that the memory address is the Safepoint poll page. And so we know that this access violation or segmentation fault is not a real crash, but it's instead related to cooperative suspension. We save the instruction that trapped into a field of the Java thread called save exception PC. The operating system also provides us with the CPU context in the state it was at the time of the trap. We can now, in the signal handler, rewrite the CPU context. That is, we can modify the instruction pointer, or RIP, to, instead of pointing to the original Java code that trapped, it will point to a specific stub routine. When the thread is resumed after unwinding all the exception handlers, the operating system reloads this now modified CPU context, and the thread continues running in the specified stub routine instead of the original Java code. This gives us an opportunity to look at the representative example of a hotspot stub routine. This one is called Safepoint blob. And by the way, when you see the term blob, it usually refers to some piece of assembly code. Since we zigzag-vied in the middle of a loop, it means that there is no proper return address on the stack. So we will need to fix that up. So we need to allocate a slot for it. The enter here is important because it means we are building up a new frame on the stack, one that is not directly related to the Java code itself. Instead, this is a meta object. And because the JVM is an implementation of the meta theory for the Java language, you will see a lot of these meta constructs intermingled with the real Java code proper. So let's call this object a synthetic or a stub frame to denote this difference. Our flags register is being pushed to the stack. And if you remember the calling convention slide, we said that stack needs to align on 16 bytes boundaries. Then the general purpose registers of the CPU context are spilled onto the stack. And in addition, floating point registers are also spilled. And if you take a look at the frame sizes for these synthetic or stub frames, you will see that they are quite large. For example, the size of this frame is 360 words, or almost 3,000 bytes. And the reason for this is, of course, that most of the CPU context is spilled. If you remember in the signal handler, we saved the address of the faulting instruction. And we will now write this address into the stack slot we allocated in the beginning. And we do this for it to become the return address. The reason for this is not only to be able to return later to the place where the code left off, but more importantly, the test instruction had an associated OOP map. And during a Safepoint, the stack must have OOP maps for all return addresses. And another important role that stub routines play is to switch between the Java ABI and the specific platform ABI. And this is also a reason why the stub frames are platform specific. And we can see now that since we're about to call into the JVM, that call would need to adhere to the platform ABI. And since for this example, I'm on Windows, we first need to allocate 32 bytes of stack space, and then we pass the thread as the first parameter in RCX. In our definition of the Safepoint state, we said that thread local GC routes for all Java threads are made accessible or published to the JVM. We also detailed that the last Java frame is an important piece to get published to the JVM, as it provides an entry point for walking the stack. But we also noted that a thread has OOPs as part of its CPU context, that is directly in registers. So therefore, a tricky problem appears, that how can the CPU context of a thread be made accessible or published to the JVM in order for it to reach a Safepoint? And the answer is right here. It's the stub frame that provides the solution to this. By spilling the CPU context onto the stack into one of these stub frames, which for all practical purposes just looks like a regular frame, the CPU context is molded into a stack frame. So indeed, we can see here that the last Java frame, or the anchor field, will be set to point to the synthetic stub frame and not to the real Java code frame. An important aspect is also that these synthetic stub frames also have OOP maps. And this specific OOP map will detail the locations on the stack for each individual register. The type of the OOP map values denotes that the stack locations really belong to the caller frame, here the Fibonacci method. And I mentioned a register map earlier, and the register map will be populated with the positions in the stub frame, and together with the OOP map in the caller, that is the Fibonacci method, the OOPs that are denoted to be placed in registers can be resolved. So this took care of exporting the context, the CPU context and the stack for this particular thread to the VM. And as we call into the VM, finally we get to set the thread state field of the Java thread to blocked, together with a full fence instruction, which is an important part in getting the thread local GC routes visible or published to the VM. The thread will now wait on a global semaphore. And after the VM thread has run the VM operation, it signals the semaphore. And when the thread resumes, it will disarm its own poll page and continue executing from where it left off. So this concludes this presentation on safe points in the HotSpot JVM. I hope you found this useful, and thank you for watching.